Hello everybody, welcome to the next video in the series of Physics at Home. In today's video, we're going to talk about Kirchoff's laws. Now there are two laws and hence this video is split into two parts. In the first part, we're going to be talking about the loop rule. So the loop rule here is stated as sum of the voltages around the closed loop is 0. Now to explore this rule here, we are gonna build this circuit. Okay. As you can notice here, in this circuit there are two voltages, V1 and V2. So the two batteries, we're gonna use, and then two resistors. Okay, so the resistors that I'm gonna choose are in the tens of thousands of ohms. Okay, so when the circuit is finished, then the next step would be to do all of these measurements. Okay, so the V1, V2, R1, R2, and then VAB, VCD, VAE, VED. All of these are the subscripts come from these numbers that are mentioned here. Okay, so at the corners, labels A, B, C, D, and then E, F. Now F here is not going to be relevant in the part 1 of the video, but in the part 2 of the video it will play a significant role. Okay, so without further ado, let's get to creating the circuit and doing the measurements. Here we see the circuit diagram, and there are two voltages and then two resistors. The two voltages are the two batteries, the 9 plus volt and then the 6 plus volt, and two resistors, and both of these are in tens of thousand. I believe this is something around 55,000 ohms, and this one is I think 72 or something like that. So why don't we just quickly check how much are the voltages, resistors. So I'm gonna put it down. $55.6, and this one is selected at K, 200K. So this 55.6K. So let's write that down. Kilo ohms. It's too bright on the other side. So yeah, 55.6, and then the other one, $74.4 kilo ohms. Okay, so now that we have these two, I'm just gonna double check the voltages. Alright, so for the 6 volt, this is the positive, this is negative. I'm gonna put the red, which is the input, and black, which is the output, in this fashion. 6.36. I'll write that down. So 6.36 volts. Let's see the other one. Positive with this side. $9.2122, somewhere around that. Alright, so we have this now. Now, the way this circuit is drawn, okay, so there are, the symbol is one long line and one short line. Again, one long and one short line. Okay, so the long line always represents the positive terminal. So this is the positive side, and this is also the positive side. Okay, and then negative are the shorter ones. So the way I'm going to hook my 9 volt and 6 volt batteries are from the positive terminal to the negative terminal. Okay. So I'm going to use my connecting wire here. So from the positive, and go to here, negative terminal. Okay. So as you can see, that's the wire from positive to the negative. Then from the positive of the 6 volt, I connect it to resistor 1. Okay. So I'm going to use this red wire here. From the positive to this resistor. Okay, so I have that. Then from this resistor, I go to resistor 2, right? So there's a connecting wire in between. All right, got that. So from resistor 1 to resistor 2, and then the other end of resistor 2 is connected to the negative of the 9 volt, right? So from here to the negative. Okay. All right. So now, currently the circuit is complete. Okay. So the current is gonna be flowing from positive here to negative to the positive to resistor 1, and then through this wire to resistor 2, and then ends at the negative of this. Okay, so that's the loop. Okay, so looking counterclockwise. So I'm expecting the currents to flow in these directions. So when I feel these out here, okay, that current in R1 and current in R2, then in R1 I'm expecting the current to go from A to B, and for R2 from C to D. Okay, so let's see. Now we need to fill out these numbers here. So VAB. So now I'm going to measure voltage. Again, I'm still there. AB would mean that A has to be my red terminal, the input, and then B has to be the output terminal. So it's going to be voltage at A with respect to voltage at B. Okay, so A end of the resistor, okay, which is this end, and then B end of the resistor is this end. So red is supposed to go here, and black is supposed to go here. 6.44 volts. That's VAB. Let's write that down. 6.44 volts. Okay. Next up is CD. Okay. So C, again, whichever is the first subscript is going to be the red terminal, and D is going to be second subscript is going to be the black terminal. So let's do that. As I can see here, then C is this end and D is this end. So CD is what we want. 8.62. Okay. 8.62 volts. Yeah. All right. Now it's also asking VAE. Okay. So A with respect to E. E is in the middle of this line, correct? That is connecting from the positive to the negative here. So we cannot use the probe on this, because it's insulated. So any of the two ends, okay, so either this end or that end, it doesn't matter. They both belong to the E. Okay, even though on the picture you must be like, okay, no, this is different than that, but the line here in between means it's a conducting wire, and nowhere here there is a change in the voltage. Okay, so A is this terminal, correct? Actually, we were saying earlier that A was this one, so we can put it here, and then E is supposed to be either here or here, correct? And to make sure that it doesn't change, we can measure it on both sides. So here 6.36 or here 6.36. Okay, so it doesn't matter where I'm touching it. Okay, not only that, but if you think that there is no voltage drop in the white wire, then there shouldn't be a voltage drop in the red wire as well. So meaning the A terminal or A point here could belong to either one end of the resistor or also the positive terminal of this battery, correct? So if I check again, remember, so this is about 6.36, right? So which is true, and I can also do it here. Yeah, 6.36. So conducting within the wire, there is no voltage drop anywhere. Okay, only at wherever they are connected. Okay, so either this terminal or this terminal again is the same voltage, and this one again the same voltage. All right, so AE is 6.36, which if we check here, that is nothing but measuring the voltage of this power supply. Similarly, when we do ED, then E with respect to D is nothing but the voltage of V2. Let's see. So E could be here to here, right? But 9.18. We are slightly different, 9.22, but it's okay. It's pretty close. So I put it here, the same. Yeah. If I put it here, I guess the same number. Yeah. So 9.18 or 9.19. Okay. A tiny bit of difference, it's fine with me. Okay. So now we have all these voltages. Now I need to measure the current that is passing through R1 and R2. Okay. Now to measure the current, what I need to do is disconnect, this wire here. So I can, remove this and essentially create move to this one here. Let's see. Essentially then create this multimeter like a conducting wire. So when you select this function here, then the multimeter inside there is a very almost negligible resistance. So it acts like a conducting wire, and the two ends of the wire are these two probes. Okay, so remember we had connected from the positive of 6 volt to the resistor here, right? So this is what exactly we do. So that current is coming out from the positive terminal, right? Then entering this multimeter and then leaving through this black terminal, the probe. Okay, and then if I hook it up here, I'm going to see current on this 118.5. So I had selected a mu 200 mu as the range. So that gives me the current flowing through R1. So forgot how much was it. 118.5 micro amps. Okay, so 118.5 micro amps. Sorry about that pen here. All right, which direction is it flowing? A to B. The reason we are certain is because I'm expecting that current to start or go through the red and enter the multimeter and then come out from the black terminal. Okay, so comes here, right? If that is correct, then I see a positive number. If I switch the two, that assuming that current is coming out from the resistor and going to the terminal A, let's see what happens. So I get the same number but negative sign now. So this negative sign is going to indicate that what my assumption is that if it is leaving from here but entering here is incorrect. The earlier assumption is correct, that it leaves from the terminal for this battery and enters the resistor. Okay, that's how we know the direction of the current. So let's write that down. It's A to B, and I'm gonna add an arrow here. That is the direction of the current through R1. So it's flowing in this direction. So for R2, I am gonna expect the current to go from C to D. Okay, so let's hook this up back. And once it's done, now I need to remove, I'm gonna do is remove this one. And how much do you think should be the current? Well, think about it. This is, nothing is changing. There is no split section. So if you think about it, it's like a plumbing, then it's the same pipe that's going all around. So whatever is the current here, I'm gonna expect the same current here, because there is no T section or something where the water will split. So let's see if I'm correct. Now the current is leaving resistor 2, enters the multimeter, comes out from black and reaches this 9 volt. Okay, 118.5, same exact value. All right, so and it is flowing C to D. Okay. All right. So this is how you perform this circuit. Okay. Now we have all the information we need, and in the next section of the video, I'm gonna show you how we can use all of this information to prove the loop rule for Kirchoff. All right. So here in the table, we see all the data that we recorded by creating this circuit right here. And at this point of time, we are gonna now explore what is the loop rule actually. The key word here is loop. And it says that sum of the voltages around the closed loop is 0. What it means that, let's say we begin at this point D in the circuit, and if you go around the circuit and create a loop, in this loop we're gonna encounter 4 items, right? 4 circuit elements, 2 voltages and 2 resistors, and then each one of these items is contributing to some voltage, whether it is added or subtracted. And how do we know? Is by using a sign convention. Okay. Here you see for the voltage here, that if this green arrow here represents the travel, just like this green loop arrow that I have created. So in our movement, if we are going from negative to positive for a battery or a power supply, then you add the voltage. If you are going in the opposite direction, then you subtract the voltage. If you encounter a resistor, and if your direction of the travel is the same as the direction of the current, okay, something like this, then you subtract the voltage, which comes from the I times R, the Ohm's law. Okay. So if you go with the direction of the current, then you lose voltage. If you're going against the current, then you add the voltage. Think about it again as, a river flowing down a hill, right? If you go with the river, then you lose height, yeah? And if you go against the current of the river, then you gain height. And height is equivalent to voltage. So let's just mention the Ohm's law. Voltage equals to current times resistance. Okay. So current times resistance is the voltage drop across a resistor. Okay. For a power supply, voltage is the voltage that we measure. Okay. Now using this, now let's see if indeed the loop rule turns out to be true. So we said that we're going to start at D. Okay. Then the first item that we encounter is the V2, right? And how are we going? We are going from the negative to the positive of the V2, correct? So plus V2. Okay. So whatever is the voltage for the V2, which was the voltage from, ED, correct? So which is this guy right here. Then we encounter the second power supply, the V1. And that one is going to have voltage AE. Again, we're going from negative to positive, so we add. And this is VED, and this is VAE. Yeah. Next item we're going to encounter is resistor 1. Yeah. And as you can see, we are traveling with the direction of the current, right? So if you're traveling with this direction of the current, then we subtract current times the resistance through which that current is flowing. Then we come to B, turn right, then turn up. And now we are going again with the current for R2, right? The current through R2. So again, that one is I times R2. Then according to the loop rule, now that we have finished the loop because we started at D and we also end at D, right? So we finished, we completed a closed loop. Then all of these items, the voltages, should add up to 0. That is the loop rule. So then let's see. All right, so what did we measure? We measured ED as 9.18. Then we measured AE, the voltage AE, as 6.36. Current was 118.5, 10 to negative 6, right? Multiplied with resistance 1 is 55.6, 10 to 3. Minus, again the same current, 118.5, 10 to 6. And R2 is 74.4, 10 to 3. So let's see how much is this. Okay, so what do we end up with? 0.135. Okay. I was expecting this number to be, much closer to 0. But it's possible that, as we can see, this 9.18 here is slightly different than, what I was expecting that number to be, about 9.22. And if we do the math here, then 9.18 plus 0.135 is about 9.3 or something. Okay. So somewhere with this voltage 2 measurement, maybe there was something missing, in the sense that maybe the battery initially was showing higher, then maybe lower, and then some number in between could have helped us, get it closer to where we want this to be. But anyway, so this is not 0, but it's pretty close to 0. So approximately 0 volts. So then we can say that if you go around this circuit, then we're getting a pretty the loop rule verified. Now, for the multimeter also, we did not have a situation where I couldn't see the value of the current, lower than this first decimal, right, or higher than first decimal. So it's possible I might have, I see only up to this point here. Also the resistance, I'd say only up to first decimal. So given that, maybe there is some, room for error. But I could be wrong. Maybe there's something else is going on. And if you think about, some other possible reason that could have led to having this voltage not exactly to be equals to 0, then, think about it. Okay. Now that we have seen the loop rule in action, maybe if you have all these pieces in front of you, what you could do is modify this circuit a bit and make it so that now the voltage 2 polarity, you switch it. So you make this as negative terminal here and positive over here, as opposed to the previous one. And think about it now. So negative and positive of the voltage 1 are here, and negative positive of voltage 2 look like that. So we connect the negative and negative of voltage 1 and voltage 2. What do you think would happen? Which direction do you think the current will flow? Will the loop rule still be valid? It would be. Check for yourself. Okay. Next week, we're going to see the part 2 of Kirchoff, where we talk about the junction rule. Have a good day.